Welcome to this lecture. This lecture will cover what is called the transportation lemma, and it will also expose us to the first concrete application of the transportation method to prove a familiar concentration inequality which we have shown using other methods, which is the McDiarmid inequality for functions with bounded differences. So let's recall from the previous lecture that a transportation inequality or a transportation cost inequality is basically a useful bound on the optimal transportation cost or the optimal cost for a transportation problem, which is defined over all couplings or transportation plans between marginal distributions P and Q. And we had this notation CPQ for it. So CPQ is just the minimum possible expected transportation cost over all joint distributions with given marginals, and any upper bound on it is essentially a transportation inequality. So how do transportation inequalities help lead to results on measure concentration? Okay, so the core part of this is because of the following result, which is called which one can call a transportation lemma. So this result essentially says that a bound on the log moment generating function of a random variable z. Okay, so any bound of the following form, which is a quadratic bound, exists for a random variable z if and only if a corresponding bound exists for the differences of expectations of z with respect to two measures q and p being bounded by the square root of the relative entropy or KL divergence between Q and P. So the statement that there is a sub-Gaussian log moment generating function for Z, for centered Z, is equivalent to the fact that for every possible probability distribution Q absolutely continuous with respect to the original distribution P of Z, we have that the expected value of Z according to Q minus the expected value of Z according to P can be bounded by some constant times the square root of the KL divergence between Q and P. So this is the transportation lemma. In fact, we've already seen one side of it in the introduction to the transportation method. We argued essentially that if we had bounds of the latter form, where EQZ minus EPZ is bounded as a function of the square root of the KL divergence, then you could get bounds in the log moment generating function, and that was basically by appealing to the variational formula for KL divergence. So that's what we will exhibit again in this proof. But this lemma essentially formalizes the fact that bounds for moment generating functions and transportation cost type bounds are essentially two sides of the same coin. So we start by recalling the standard Gibbs variation formula for KL divergence, which we have seen and derived in earlier lectures. It states that the log moment generating function of a centered random variable is in fact equal to the solution of a optimization problem over all absolutely continuous distributions Q with respect to P of lambda EQZ minus EPZ minus DQ with respect to P. So for showing the forward part, which is the only if part, or the necessity part. So if we assume that for all lambda the centered log moment generating function right, so by the way, we will refer to the log moment generating function of Z minus EZ under P as this psi function. So if for all right. So, for all lambda, we have this quantity being bounded by v lambda square by 2, which is the first statement here. Right. In fact, we can just say that for all lambda non-negative, then for Q absolutely continuous with respect to P, we can use the Gibbs variational formula to give us that dQp is greater than equal to. So, we just so since the log moment generating function is the supremum of this, we can always apply this for any q less than absolutely continuous with respect to p, and we will only get a quantity that is lower than the log moment generating function, and we can rearrange terms algebraically to get that dqp is at least lambda times eqz minus epz minus v lambda square by 2. Okay, which is an upper bound on the log moment generating function, and we can just treat this right hand side as a function of lambda. So, if we just maximize the right hand side of this expression, in fact we can just maximize this over over lambda gives to give dqp greater than equal to eqz minus epz the whole square by 2v. Okay. Now, for the other side, for the if part or the sufficiency part of the lemma. So, if for all absolutely continuous q, the hypothesis is that the expected value of z with q minus epz is at most square root 2v dqp, then we have that for every lambda non-negative, the log moment generating function of z with respect to the measure p is at most. So, we just substitute the upper bound for eqz minus epz in Gibbs variational formula. So, we get lambda square root 2v dqp minus dqp, and we can just treat this as a maximization problem over the variable dqp or square root dqp. So, the supremum over x unconstrained lambda square root 2v into x minus x square, and this by exact analytical minimization gives you the closed form answer lambda square v by 2. So this is the content of this transportation lemma. In fact, this lemma is little more general than what we wrote than what we just wrote. So, we will just make a remark here that the lemma extends to any nice enough function g. So, essentially we need g to be convex and with smooth derivatives as follows. You can check this in the textbook for the more general version. So, for all lambda non-negative, if we have the log moment generating function of z minus ez being bounded by g of lambda, some function g of lambda, this is equivalent to the statement that for all absolutely continuous q, epz minus eqz is bounded above by the dual function g star, the Legendre dual of g, its inverse applied to dqp. And so this the specific lemma we wrote above is just a special case of the more general result when the g function is the quadratic function. Okay. So with this transportation lemma in hand, this transportation lemma essentially gives you the bridge between transportation type inequalities like these and log moment generating functions of random variables, from which we already know there is a route to go to showing tail concentration using the standard Chernoff technique. So we'll now come to what is probably the most important initial application of the transportation method to derive something that we've already seen before, which is McDiarmids inequality, or the bounded differences concentration inequality for stable functions of independent random variables. So we've derived McDiarmids inequality using other techniques like the entropy method, and even much more in a more basic sense by using the Azuma-Hofding method. But here we will derive it through the lens of the transportation lemma. So we'll assume the same hypothesis as McDiarmids inequality, which is that there is a function f defined on n variables which satisfies the bounded difference property with a set of constants, one per dimension, c1 through cn. So it means that if you keep all but one coordinates xi the same and you wiggle xi, the function value can change by at most an amount ci. Let P be a product distribution over Xn, that is to say that f acts on a bunch of n independent random variables, and let Q be any other distribution. So we can start by saying that for any coupling or joint distribution yielding marginals P and Q, we can always write that EQFX. So recall that we basically want to use the transportation lemma to get a bound on the log moment generating function, and the central object on which we need an upper bound for using the transportation lemma is expressions like these: EQFX minus EPFX. So think of fx as z. So you can interpret this. So this is the power of the coupling method. So you can interpret this as the expected value of y distributed according to q of fy minus the expected value of x distributed according to p of fx. Okay, the same random variables expectation being taken under two different measures, and we can actually now use the coupling which is boldface p to actually write things under a common expectation as the E without any subscripts, which is sort of attached to this P of Fy minus Fx. So it's a single expectation that is equivalent to the difference of two different expectations. So this is just because P is a coupling between P and Q. Okay, so the individual marginals are the right marginals, and now that we have Fy minus Fx inside the expectation, we can actually use almost sure properties or pointwise properties of f, which in this case is the bounded difference property, to write that this expectation, in fact the inner term is bounded almost surely, so applying the expectation doesn't change things. I equal to 1 to n, we know that this almost sure bound holds. This is by the bounded differences property we assumed. And this now sets the stage for this to look like a transportation cost inequality. Okay, so this is exactly equal to, if you interchange summations and expectations, the sum of Ci times the probability that Xi and Yi are different. Okay, and we can further upper bound this by using something like Cauchy-Schwarz sum over all I of Ci square under the square root into the sum over all I of the squares of these probabilities under the joint distribution P. Okay, this is let's say by using Cauchy-Schwarz. Okay, and so what we have achieved using this exercise is an upper bound on EQF minus EPF in terms of some constant, which is the square root of the, which is the L2 norm of the C vector, the bounded difference vector C, into some other term. So we will only benefit if we can upper bound this remaining, the last term here on the right, in terms of the KL divergence between P and Q, the distributions P and Q. Okay, so that will help us to directly use the transportation lemma and push things through. So by the transportation lemma, it stands to reason that it is enough to show that, for instance, there exists a coupling. So if we show that there exists a coupling, a nice enough coupling that we can find P between P and Q, such that the sum over all I of the probability that xi not equal to yi whole square is, let's say, at most some multiple of the KL divergence dqp divided by 2. Okay, so it is enough to show this kind of property to get. So using the transportation lemma, we can just push this through to get the log moment generating function of z at lambda being bounded by I equal to 1 to n Ci square into lambda square by 8 for all lambda non-negative, which in turn will imply a right side tail bound for the deviation of f of x about its mean. Okay, by Chernoff for sub-Gaussian random variables, the original PV probability of f of x, the random variable f of x, exceeding its own expectation by a number t is at most, it has a sub-Gaussian type tail modulated by the constants Ci. Okay, so the main thing that the transportation lemma assures us is enough to show is a statement of the following form, that one can couple P to Q while keeping this sort of transportation cost like expression on the left not more than a multiple of its KL divergence. So this statement or property that we require, which we'll call hash, is essentially a inequality involving transportation costs because for each I probability, we have already seen that for each specific I, the probability that xi is not equal to yi is actually an expected transportation cost, where the cost structure is given by the indicator that xi not equal to yi for every individual tuple xi and y. Okay, so it's the Hamming cost, Hamming transportation cost, and so this is essentially an inequality that involves transportation costs and a bound on them. Okay, so the strong result that Marton actually established is basically this exact result, this transportation cost inequality that allows us to prove successfully the bounded differences inequality. So in fact, let us remark that this property, the existence of such a coupling star, was shown affirmatively it was answered, so was shown to hold by first time by Cattell and Martin in 1986, and there have been several developments after this in the use of transportation inequalities to bridge to concentration of measure inequalities. So let's go ahead and study Martin's transportation cost inequality, which is the last piece remaining in this exercise to successfully derive McDiarmids bounded differences inequality. So here's Martin's transportation cost inequality. It says that if you have a bunch of random variables x1 through xn distributed independently according to the joint measure p, so p with the ith marginal of p being denoted as pi, p1 through pn, and q is any absolutely continuous distribution with respect to p for the set of random variables x1 through xn. In fact, let's assume that y is a bunch of random variables, n random variables distributed jointly according to q. Then there actually exists a coupling between p and q for these n random variables x1 through n and y1 through n, satisfying the property that the summation of the disagreement probability squared over all I between xi and yi is at most half times the KL divergence between q and p. Okay, so this is exactly Martin's transportation cost inequality, which completes the derivation of McDiarmid's inequality via the transportation lemma, and finally using Chernoff. Okay. So the last part of this lecture is going to be the proof of Martin's transportation cost inequality, where again we will actually build or find an explicit coupling which satisfies this property, just as we did with the maximal coupling, for instance. So let's go ahead and do the proof of Martin's transportation inequality. The proof is going to be by induction over the number of elements n, over the number of random variables to be coupled. So for the base case, this is itself an interesting problem. It's the n equal to 1 case, and we already know by the maximal coupling lemma that there exists one nice maximal coupling which can couple x1 through y1, px1 not equal to y1 equal to dtvpq. Okay, so there exists a p which can couple x1 to y1 such that this holds, and so all that is required to show is that the square of this quantity, which is the total variation distance p, so p1 and q1, I will say. Okay, so all we need to show by the theorem for the base case is that the square of the total variation distance is at most half the KL divergence, and that is exactly what is Pinsker's inequality, which we will now prove. So the base case for Martin's transportation cost inequality is Pinsker's inequality. So it is a generalization of Pinsker's inequality. So which simply says that for any q absolutely continuous with respect to p, the total variation between p and q square is at most half of dqp. Okay, and the proof is by appealing to the transportation lemma. So let's put A as the, let's define A as the set where dq by dp, the Radon-Nikodym derivative of q with respect to p, or in the discrete case, so this is larger than equal to 1. In the discrete case, A is just the set of all elements whose q probability is at least the p probability. So that dTV, the total variation distance between P and Q, is QA minus PA, which one can write equivalently as EQZ minus EPZ for the random variable Z being defined as the indicator random variable for the set A. Now, by Hofting's lemma, for the bounded random variable Z, which takes values only between 0 and 1, we have that the log moment generating function of Z, if we center it, is at most, it's a sub-Gaussian log moment generating function. Okay, lambda square by 8 is a bound for it, and so using the transportation lemma, you can convert this into a bound on the EQZ minus EPZ. So this by the way holds for all lambda. So it follows that EQZ minus EPZ must be at most half DQP. Okay, and that finishes the lemma, because EQZ minus EPZ is exactly the total variation distance between P and Q. Okay, so the base case is done, which is the familiar Pinsker inequality that relates that helps us control total variation distance in terms of the Keil divergence. Now, for the induction step, let's assume that the claimed inequality in the theorem holds for n equal to k. So, suppose the inequality in the theorem, let's call it, so we already called it star. So, suppose that the statement star holds, the conclusion of the theorem holds for a collection of k random variables x1 through k and y1 through k. That means there is a coupling that gives you the desired property. So, we will just extend that coupling. We will extend the coupling between x k. So, x superscript k will be used to denote x1 through xk, the collection of variables, random variables x1 through xk, and y1 through yk to get so we will extend this coupling between these random variables to a larger collection x up to k plus 1 and y up to k plus 1 to get star to hold again for the larger correction. Okay, so for n equal to, precisely for n equal to k plus 1. So, the key to doing this extension of the existing coupling is as follows. So, let us first couple the last part. So, build a coupling. So, let us build a grand coupling of the k plus 1 collection of random variables, x from 1 to k plus 1 and y from 1 to k plus 1 as follows. So, first for any fixed y, so for any fixed configuration of the first k y's, so the first k y's, let us denote them as small y1 up to small yk or small y superscript k. Let us define pyk. So, p subscript yk, you should read this as bold p given the configuration small yk, small y superscript k, as a coupling. So, let this pyk denote a coupling that couples the k plus first marginal of x, which is pk plus 1, with the k plus first joint distribution of k plus first conditional distribution of yk plus 1 given the previous yks. So, we denote this as q, the distribution, the q distribution of the k plus first y given that the previous k y's have been observed to have configuration small yk. Okay, so let this be a maximal coupling of these two distributions of so as random variables we can say it's a maximal coupling of x k plus 1, the single random variable x k plus 1, and y k plus 1 given y k equal to small y k. Okay, we always know by the maximal coupling lemma, we know that such a maximal coupling always exists. Okay, such that the discrepancy probability between these two random variables that it couples is exactly equal to the KL divergence between the marginals that it couples. Okay, so so just get hold of, so for any given conditioning or fixed past configuration small yk of the y's, let pyk denote a maximal coupling that jointly delivers a pair xk plus 1 and yk plus 1 given that small yk has happened, okay, and which also achieves the total variation constraint with equality in the transportation cost problem. So, we will write it down explicitly later. So, okay, so given the past y's, this basically gives you a joint pair, a fresh joint pair xk plus 1 and yk plus 1. Okay. Now, having done this, take a coupling P, let's call it that couples xk, the first k x's and the first k y's. So, this couples P xk and q yk. That is guaranteed to satisfy the inequality star. For n equal to k. We know that this is guaranteed to exist by the induction hypothesis. So, grab hold of any coupling between xk and yk that satisfies the inequality star, and we will now use this conditional extra coupling to extend the original coupling pxk yk, okay, and extend it to a coupling. Let us call the new coupling pxk plus 1 yk plus 1, coupling these two sequences with one extra element each, which we will insist couples pxk plus 1 and qyk plus 1 by, so it's defined in the usual manner. So so symbolically what one can say is that if we want the joint distribution on xk plus 1 yk plus 1, how you can generate a joint sequence xk plus 1 comma yk plus 1 with the respective marginals is that you first generate xk yk. Okay, so you first generate xk comma yk using the existing coupling that is guaranteed by the induction hypothesis. Now, having the yk sequence in your hand, the previous y all the way from 1 to k in your hand, you use this new extra coupling pyk. So, you take small yk as the actual yk that has happened in the past, and using that you can basically generate a new xk plus 1 and a new yk plus 1 conditioned on the exact yk in the past. There is no condition required on xk in the past, because the new x is going to be independent from the past x's. So, what you do is you take, firstly you generate x and y up to length k, and then you generate the p yk. So, you generate xk plus 1 and yk plus 1 conditioned on y all the way up to k using the extension coupling, the conditional coupling, to basically give you a sample from the entire sequence x up to k plus 1 and y up to k plus 1. So this part gives you xk and yk, and this part by definition of pyk gives you a new tuple xk plus 1 and yk plus 1 that you can append to the existing sequence xk yk. So now what we can write is that by the maximal coupling property of the the tail coupling p yk for each possible value of the configuration in the past y superscript k, we have that. So this is the maximal coupling property, which ensures that the probability under this yk of x k plus 1 being unequal from y k plus 1 given xk equal to xk and y sorry, so we don't need the subscript pyk. This is under the extension coupling. So in fact, let me just be more precise and say that p under xk plus 1 yk plus 1 that we just constructed of xk plus 1 not being equal to the k plus first symbol of y, given the past of x is small xk and the past of y is small yk, must be equal to the total variation distance between the distributions that the tail end coupled, which are pk plus 1 and the conditional distribution of yk plus 1 given yk equal to yk, small yk. And by Pinsker's inequality, we know that this is at most square root of half the KL divergence between the conditional distribution q yk plus 1 given yk equal to yk with respect to the pk plus 1, the distribution of the k plus first x by Pinsker, which is just a one-dimensional inequality. And so we can just take expectation over the conditioning here to make it a single probability. So this implies that when we take expectation over the past of x and the past of y up to time k, we get that under, so of course I am omitting the subscript xk plus 1 yk plus 1, but all of this is under the new coupling for x up to k plus 1 and y up to k plus 1. So this satisfies the property that probability xk unconditionally xk plus 1 not being equal to yk plus 1 is at most the expected value under qyk of the square root of half the KL divergence qyk plus 1, the conditional distribution with respect to pk plus 1 and this by Jensen's inequality for the concave square root function is bounded by the square root of half the expected value of the divergence of the conditional divergence. Okay, right. So this is by Jensen's inequality. So finally what we have is that the statement star for n equal to k plus 1, its left hand side is simply the sum over all I going from I to k, 1 to k plus 1 of the probability squared that xi not equal to yi. So you can split this into the sum from 1 to k and then the k plus first term. The induction hypothesis gives us a bound for the first k terms, the sum of the first k terms, as d q y k with p x k. This is by the induction hypothesis. Plus the additional term, the last square term at position k plus 1. Which we just bounded above as half by half the KL divergence between q y k plus 1 with respect to p k plus 1 conditioned on q y k. It's the expected KL divergence which we've just written under this notation. So it's the conditional KL divergence of q y k plus 1 given the entire past of y with respect to p k plus 1 and then averaged out across the past q y k. And this precisely by the chain rule of KL divergence equals what we want, which is d between q y up to k plus 1 and p up to of x up to k plus 1. So this is by the chain rule for KL divergence, which you have seen earlier. And that completes the proof. So this was McDiarmids inequality or the bounded difference inequality derived using a very different method, which is via the transportation lemma. Thank you.